This is the equation for computing one frequency bucket of a discrete Fourier transform labeled k. Note that it requires one full pass over the input signal x, so if you want to get values for all big N buckets, you will have to perform big N squared operations. As a side note, however, observe that the bucket index k does not actually have to be an integer. We will like it to be an integer for purposes of deriving the Fast Fourier Transform, but the fact that it doesn't have to be can be useful in some other applications. Now, we can do a little bit of reindexing to split up the terms of the summation into two different summations over the even and odd indices of the original signal. This does not change the terms we compute, or the final result at all. It just rearranges the order in which we compute them. Note that while adding 0 or multiplying by 1 don't do anything, I will keep these operations in the formulas just to highlight the parallelism between different terms. Now, we have some sums in the exponents, and it will be useful to extract out the constant terms from those sums. To do that, we'll rewrite exponentials of the form w to the power of 2kn plus zk over big N as w to the power of 2kn over big N times w to the power of zk over big N. After that, we can replace a multiply by 2 with a divide by 1/2, which allows the n-dependent terms to match the reindexed summation limits. Pulling out factors that don't depend on the summation index n, we get this simplified form, which shows how we can recursively calculate discrete Fourier transforms of the even and odd subsequences, and then combine them with the bucket-specific twiddle factors of w to the power of k over big N to get the transform of our original signal. Now, most explanations of the Fast Fourier transform that I have found effectively stop here and say, look, you can divide the problem in two, and then you can divide those subproblems again, and divide and conquer algorithms are fast. Except, at this point, we haven't actually saved any work. We are still calculating exactly as many terms of the sum, just in a weird order. And splitting those subsequences again won't change that. So what actually makes the Fast Fourier transform fast? The key insight is that the Fourier transform is periodic. Because w to the power of 1 is 1, if you calculate a bucket with index k plus big N, introducing a factor of w to the power of big N over big N equal to w to the power of 1, it will have exactly the same value as a bucket with index k. Now, how does that help us? Well, let's see what happens if we try calculating a bucket value with the index k plus big N over 2, with our even-odd split formula. It starts out looking like this. Rewriting our exponential sums, we get this. Now, the summation index n is always an integer, and w to an integer power is always 1, so we can just drop those factors. Now, if we put this next to our original formula for the bucket with index k, we can see that all of the plus big N over 2 terms have been eliminated, and we have exploited the periodicity of the subtransforms to get a set of equations that has common summations reused between these two buckets, which are in fact different in the original larger signal. If we then simplify things by removing the zeros and ones, we get the standard formula for the recombination step of the radix 2 Fast Fourier transform. You can calculate the even summation and the odd summation once, but get two bucket values out at a separation of n over 2, at the cost of multiplying by a bucket-specific twiddle factor. Now, what do I mean by radix 2? Well, this isn't the only Fast Fourier transform. It only works if your input signal has a length divisible by 2, and that is true of most actual FFT implementations. If the input length allows it, however, we can, mathematically, divide by any number we want. So, here's the reindexing formula for a radix of 3. And here it is after simplifying to pull out the twiddle factors. Now, we can use these three subsums over the indices congruent to 0, 1, and 2 modulo 3 to calculate three output buckets. First, we have the formula for k plus big N over 3, which simplifies like this. And here is the simplified formula for the bucket with index k plus 2 big N over 3. If we line all of those up, we can see that, just as in the radix 2 case, all of our subsums only have to be calculated once, and then we just have to multiply each subsum by the appropriate bucket-specific twiddle factors to get all three buckets for the price of 1 and a bit. Note, however, that we don't have nice integer exponents anymore, so we don't get the same convenient simplifications where some of the twiddle factors are just negatives of the others. So, although the radix 2 case is the simplest and most efficient in practice if you can use it, you can actually use any radix you want and get some level of divide and conquer speedup on any input signal with a non-prime length, if you're willing to actually code it up.